Welcome all to my Natural Sciences Research Project presentation. Before I begin, I want to thank you all for being here today, particularly under the circumstances we find ourselves in. Today I'll be walking you through how I was able to fabricate a power source small enough to be incorporated into smart textiles using mechanical motion alone. I will start this by outlining the preliminary research taken, particularly with what a Triboelectric Nanogenerator is. Then I will guide you through the experimental process and demonstrate how we can characterize these devices. I'll then present the data obtained and indicate where possible any conclusions can be drawn. And finally, to wrap up the talk, I will touch on avenues to continue this work. The overall aim of this project was to produce and test materials used in a Triboelectric Nanogenerator for applications within e-textiles. Since the dawn of sewing and weaving, technology has always led developments in clothing. And today, in the 21st century, wearable technology will be the next big step. With the e-textile market forecast to be worth over $1.4 billion by 2030, there really is no surprise that every industry, from military to fashion, chooses to benefit from this new frontier. Healthcare, however, stands to benefit the most, as the promise to monitor human vitals like cardiac potential and blood glucose levels is invaluable. To achieve this, we must investigate ways to meet the difficult standards of clothing that electronics often struggle with. Successful devices must be flexible, durable enough to survive washing, and small enough as to not compromise a user's mobility. When choosing how to power these sensors, it's also important to consider that conventional batteries will often need replacing and contain materials toxic to both humans and the environment. For this reason, it is key to find novel ways to power such technologies in both a safe and sustainable manner. One solution is a Triboelectric Nanogenerator, or more colloquially known as a TENG. This self-powered device is capable of harvesting kinetic energy and converting it into electrical power. It does this with a reasonable enough conversion efficiency for small power applications, as seen by this demonstration powering a digital watch. It does this by harnessing the phenomenon of static electricity. This is otherwise known as the triboelectric effect and can be described as so. When two materials come into frictional contact with one another, they exchange electron charge, depending upon which material has the greater affinity to electrons. This creates an uneven distribution of charge, which when connected up to a circuit can induce a potential between the electrodes. The larger the difference in electron affinity, the greater the overall charge. This is important when deciding what materials will interact with one another. TENGs can operate in different modes also, each with their own advantages. The video demonstrates a lateral sliding mode, while the diagrams show a vertical contact and single electrode mode. The vertical contact mode is most used in TENGs as it best complements the nature of human motion, and was chosen for this investigation because of its simplistic design. The next step to consider is electrodes compatible with the TENG. Graphene is a 2D hexagonal arrangement of carbon atoms that show huge potential for applications into e-textiles owing to its high performance properties. The orbital arrangement exists such that the PZ orbitals, kept perpendicular to the plane, as seen in the image on the right, are constantly kept half-filled. This means when pi bands are formed from pi bond hybridization, electrons are able to move freely across the structure, making graphene a great conductor of electricity. Its structure also makes it stronger than steel, flexible, and highly transparent. Graphene can be obtained by various methods, but typically devolve into two categories. The bottom-down approach, which sees carbon atoms deposited one by one on a substrate to form a monolayer sheet of graphene. This can be done via chemical vapor deposition, or CVD, which will be covered later. Or the top-down approach, which cleaves layers off in chunks of graphite. Exfoliation remains the process that produces the lowest number of defects, and was the method responsible for graphene's discovery back in 2004. Let's look at how the devices are set up before we delve further into the methodology. Now, the two chosen triboelectric materials were polydimethyl siloxane, PDMS, and polymethyl methacrylate, PMMA. PDMS is the most commonly used triboelectric material in TENGs due to its high electron negativity and can have its surface functionalized to improve potential capacitance. PMMA is the triboelectrically positive material that charges should transfer away from. This sits atop the graphene electrode obtained either from shear exfoliation or chemical vapor deposition. Their respective performances were compared to identify the more suitable process to use in this teng. The substrate type to hold the graphene was also a variable being tested. Polypropylene fibers, PP, and polyethylene terephthalate, PET sheets were chosen for being lightweight, cheap, and demonstrated a reasonable ease to coat with graphene. The teng circuit is finally connected using copper tape and silver paste, and a multimeter capable of recording the teng's open circuit voltage and short circuit current is inserted to quantify the device's electrical properties depending on the desired configuration. The final step is what provides the frictional contact needed to power the teng. The device is placed within a vertical sliding machine and is operated at varying speeds and distance separations. From this, we are able to test 4 devices by varying both the graphene and substrate type. These are CVD-PET, CVD-PP, SEG-PET, and SEG-PP. The CVD graphene was made in a low-pressure, high-temperature quartz oven. Methane acts as the gaseous source of carbon, argon gas purges the chamber of contaminants, and hydrogen aids the carbon deposition. A copper sheet is inserted in the oven and brought up to a high enough temperature to cause carbon to deposit on both sides of the copper. One side of the sheet is protected from oxidizing the graphene by spin coating PMMA on top. To isolate the graphene layer, the copper is dissolved away using a solution of iron chloride, and once the graphene is cleaned with water, it can be dipped onto the substrate for further use. Shear exfoliated graphite follows a different process. Graphite flakes, water and sodium cholate are first shear mixed at high speed before centrifuging further. This isolates the graphene in suspension and is eventually separated out from the remaining waste graphite chunks. The new SEG solution is filtered over a Buchner funnel and Teflon membrane, eventually leaving a dark disc of shear exfoliated graphite. The membrane is carefully transferred over a warm hot plate containing the substrate and placed face down after several sprays of isopropyl alcohol. The IPA aids the transfer onto the substrate, and once dry, the membrane can be peeled back to reveal a successful transfer, as you can see for both PET and PP fibers. The substrates can undergo a UV ozone clean prior to IPA transfer. Oxygen radicals bombard the surface and make the substrate more hydrophilic, improving adhesion to aqueous coatings. Preparing the top PDMS contact is relatively simple and just required drop casting a PDMS solution onto some copper tape, leaving to desiccate and then cutting up as desired. For the bottom PMMA graphene component, they are first cut down to fit on the machine mount. A silver epoxy resin is then smeared on the edge of the device with a small strip of copper tape going on top. This was done to make the contact between the graphene under the PMMA and the rest of the circuit. After a quick dry in the oven, all samples were spun coated further with PMMA to reach a thickness of 800 nanometers. This meant 1 coat for CVD samples and 2 coats for SEG. A swab of warm acetone then removed any PMMA on the copper contact. And then the devices are now ready. 3 of each 10 configuration were produced in order to isolate potential anomalies when characterization was underway. At last, we can test our tengs. As you can see, this device is currently running and outputting voltage data in LabVIEW. The PDMS is on the top mount with the main PMMA device on the bottom mount. Using the multimeter hooked up to the machine, we are able to record short circuit current, open circuit voltage, and attempt to calculate the power density when variable resistors are connected in parallel to additional voltage readings. The power density is a key part of tengs in the literature as they indicate how capable they are in powering small devices. Further readings were taken at different oscillating frequencies and with increasing distances between the PDMS and PMMA. The data is then saved into a CSV file for later data analysis. Data obtained will now be presented here, starting with the bar charts depicting both the current and voltage readings at varying frequencies. The first conclusion that can be made is the positive trend between data readings and the frequency of vertical oscillations. This is to be expected, as there are more contacts being made per second between the PDMS and PMMA, meaning more charge flows through the circuit. When identifying the better performing configuration, it appears to be the shear exfoliated graphite on PET, with peak readings of 24 volts and 0.61 microamps. These values do seem to fall within the range that standard Teng devices have been reported before. However, it was expected that CVD would perform better than SEG. According to preliminary experimentation and in the literature, CVD should carry charge better because of its uniform tri-layer structure. However, papers also exist suggesting CVD as inferior due to its energy-intensive process that also lacks scalability. SEG-PP also performed rather poorly in current data. A reason for this could be to do with any absence of SEG on the device after the IPA transfer process. This would make the conductive travel path more difficult to traverse across the device. What conclusions can we draw from the distance separation? These series of line graphs indicate the percentage change in voltage and current readings and increasing distance separations when compared to its first reading. Knowing prior that the better readings occurred at higher frequencies, all readings taken here were at 5 Hz. The graph seems to suggest that current increases with distance separation, particularly for CVD samples, but is seen to decrease with voltage. We are unable to draw any conclusions from this as triplicate readings were not carried out at this time owing to time constraints. It is worth noting, however, that prior papers looking at PDMS Tengs with aluminium electrodes saw a positive trend for both current and voltage at greater distances. In the last set of graphs, we attempt to calculate the Teng's peak power and power density. Peak power is found using Ohm's law and the power formula to get power is equal to the open circuit voltage squared divided by the resistance. This was achieved using a variable resistor across the Teng ranging from 1 kΩ to 10 megaohms, with voltage readings being made each time. The chart indicated the peak power occurs within the 1 kΩ to 100 kΩ range. It's not yet clear if 10 kΩ is the peak, as more further data points are needed in that area. We attempted to rank the electrical output of the Tengs through power density, but when comparing values to a review paper, our results appear roughly 2 orders of magnitude larger than the one stated. The PP fibers show larger readings as only one fiber was placed across the Teng's operational area, despite the entire area still being measured. Reports exist of power densities in the several hundreds watts per meter squared, so it's possible that our devices were better performing than expected, but also likely a systematic error that was present and could not be resolved. Producing these nanogenerators involves taking into account many variables. One often overlooked factor in the literature is the thickness of the triboelectric material used. Unknown thicknesses can alter the results dramatically, making reproducibility difficult. The thickness of our PDMS could not be determined due to the difficulty in drop casting such a viscous fluid. The graphene adhesion to PET and PP fibers were also prone to variability, often having no discernible way of telling why a transfer was successful or not. Applied force is also overlooked as a variable, as programming the vertical contact machine to use the same force each time is difficult to control when samples are constantly being replaced and changed. Now, to conclude, we have achieved the goal of producing and characterizing triboelectric nanogenerators using 2 different graphene and polymer substrates. All were functional and able to provide enough charge to be considered a viable option to integrate within e-textiles. However, there was still issues present that mainly involved the device's durability and effective power. CVD didn't perform as well as expected due to unpredictability and high accuracy to achieve working samples. For this, SEG appears to be the preferred graphene type as it's less energy intensive and more scalable. The PET substrate gave more reliable results owing to its better adhesion and greater applicable range, but PP fibers still show promise as the first steps toward textile integrated Tengs. Next time, a standardization procedure should be made that guarantees improved Teng performance. These include controlling material thickness, consistent applied forces, regularly check the quality of graphene, and improving levels of success for substrate adhesion. The procedure could also involve identifying and testing other triboelectric materials and substrate types which may appear more favorable to the chosen setup. A final suggestion would be to simulate a TENGs using computer software. This could compare theoretical power output of a TENG prior to actual physical experimentation. Thank you for listening.